Good morning, good afternoon, or good evening, wherever you're joining us from around the globe. A very warm welcome. This is the fourth event in our OpTek webinar series, and today's session is titled Laser Processing of Optical Fibers and Components. Before we get underway, a quick housekeeping note: today's session is being recorded. There'll be time for questions at the end, but you can send them in at any point by using the question box at the top right-hand corner of your screen. We'll gather those and answer as many as we can during the question and answer session at the end. My name is Alan Colman. I'll be your host today. I'm the QHSE and UK Site Director here at OpTek. My background is in the semiconductor sector, both here and in the UK and overseas, where I worked across equipment engineering, sales, and commercial development. Before joining OpTek, I served as QSHE Director at a hand tracking and haptics technology company based in Bristol. Before we dive into the technical side, let me briefly introduce OpTek, who we are and what we do. OpTek is a global leader in precision laser processing solutions. Our headquarters are in Abingdon, Oxfordshire, and we also have facilities in Greenville, South Carolina, Boston, and Dongguan, China. Abingdon is home to our machine builds, micromachining, and R&D teams, developing custom laser processors for systems for an incredible range of materials, from ceramics and polymers to delicate organics. If it can be machined, there's a good chance we've done it. Our roots lie in optical fiber processing, tasks like machining end faces, stripping cladding, and enhancing yield and optical performance. But our capabilities now go much further. We support customers throughout the full life cycle of laser processing, from early stage R&D and prototyping to fully automated production systems. We often work with sub-micron, 300 micron features, delivering everything from compact desktop solutions to multi-ton, multi-laser 5-axis systems, the largest of which weighs 7 tons and achieves sub-micron precision. Across the Atlantic, our Greenville, South Carolina site serves as OpTek's Fiber Center of Excellence. The team there focuses on advanced fiber optic processing and assembly, including stripping, cleaving, lensing, and splicing, as well as the fabrication and alignment of fiber arrays. Greenville also supports process development, prototyping, and production across telecom, medical, defense, and sensing markets, while providing integration, training, and technical support for our North American customers. As part of the financially strong Humanetics Group, OpTek is able to undertake long-term, high-impact projects with confidence. We're proud to hold certifications including ISO 9001, 14001, and in our UK and China facilities, ISO 13485 for medical applications, reflecting our deep commitment to quality and sustainability. Today, we'll be exploring laser processing of optical fibers and components, and I'm delighted to introduce my colleague, Chris Randon, our Business Development Manager here at OpTek. Chris will be guiding you through some of the most exciting developments in capabilities in this area. I'll be back with you later for the question and answer. So without further ado, Chris, the floor is yours.
Thank you very much, Alan. So I thought I'd start by giving an overview of mechanical cleaves. Mechanical cleaves are prone to tool wear and need skill and attention to detail. If the blade is new and you get a sharp scratch or crack, that will propagate well and you end up with something that looks like the Japanese flag here. As the blade blunts, cracks do not propagate as well, leading to an increase in hackle, which you see here, misting. This is not so much a problem for single mode fibers, but for large core multi-mode fibers, it can be. Also, controlling the tension of the fiber during that crack propagation is a problem. And if you end up with the wrong tension, you can end up with something that looks like the end that you see here. You can also quite often get lips, and we'll talk about that later. Angle cleaves are possible by mechanical methods using a twist and snap technique, but these are typically limited to 8 degrees or less. You also, using standard tools, need about greater than 10 millimeters of fiber to make a cleave, whereas in laser cleaving, we can work with a few hundred microns. Here's some examples of the laser cleave process. It's contact-free, it's not prone to tool wear, it de-skills the process and is well suited to automation. You can see here that we do get a different geometry from the standard square edges that you get on mechanical cleaves, the corners are rounded, and that's beneficial for some applications, and it's suitable for high volume. On our higher end tools, you can actually control the geometry of the cleave process. So we can go from very square cleaves, which you see here, which are very good for fusion splicing applications, to rounded edges, which are good for a physical contact application. These rounded cleaves can also be quite useful if you're in a mechanical splice and you have a lip on the other side of the fiber. Our tools are deployed quite extensively in the active optical cable market. So what is an active optical cable? That's something like optical HDMI, optical USB, optical Thunderbolt, and inter-rack communication parts. So that would be a standard Lightning or USB interface going into an ASIC, which then links to a VCSEL or a PIN diode for high-speed communications. So whereas electrical optical cables are normally limited to about 5 meters in length for high data rate communications, these can be used up to 300 or 400 meters, so are suitable for deployment in airports and shopping malls, etc. The customers that have these tools are in quite large scale production volumes. So those customers will have typically between 2 and 11 units. As well as doing flat cleaves, we can cleave large angles. So we can get anything from 0 degrees up to 50 degrees. And we can also cut that angle with respects to external features with very good reproducibility. And you can see on the video here a 45-degree cleave, which we've done on our LC3500 series. And then at the bottom here, you can see an example where we've launched light axially, and due to the total internal reflection nature of the cleave that we've put on at 45 degrees, we get emission at 90 degrees to the fiber. As well as cleaving, we can also strip the strip materials, that being acrylate, omisa, or polyimide. We can do a window strip, which is useful traditionally in butterfly packages for an S-bend to remove tension during heat, doing thermal cycling, and non-round waveguides. This was quite a thing a few years ago in the laser welding market. We can also do arrays and strip polyimide. In stripping the polyimide, using the laser, we end up with very low carbonization, no delamination, and very, very square corners or well-defined corners. The same is true on acrylate, and that is good if you need to apply coating post-process, such as metallization. We should also mention here that we're able to etch down to the cladding and the core, and we can drill fibers as well, or structure the core once we've taken off those coatings. We're also able to fuse caps onto fiber, so that be end caps to reduce power density, or lenses to collimate, or a mixture of both. We have this fusing technology, which in theory allows us to attach to a piece of quartz as big as you can make. Previously, that's been putting arrays of parts onto a 1-inch optic. Once you've end capped the fiber, you need to cut it to length so it performs as expected. With the LaserCleave systems, especially our 3500 platform, we're able to identify the splice joint, example shown here, and then cleave to length. So for a collimation application using a grin lens, we might want to cut at the quarter wave pitch, expanded beam product to where the fiber the light has filled the core. As well as end capping, we can also directly machine lenses onto the end of fiber, be that conical lenses, spherical, spheric, or wedge. How our process differs from polishing is that we're actually able to measure light on the fiber, so you see some far field patterns on the system, and trim the lens in situ, so we should end up with far better coupling to your waveguide. So we'll talk now about a couple of applications. One of the biggest applications of laser cleaving is in the pre-polish of connectors. So why would you laser cleave? Well, in many cases you want to automate and de-skill production. So typically mechanical cleaving is operator and tool dependent. Also this epoxy bead, you see here an example, is very much dependent on your dosing technology and operators. So if you then scribe here, snap the fiber and then air polish, you end up with a lot of variance by mechanical methods. Whereas with the laser, in one pass, you cut through the epoxy in the glass with very short protrusion lengths, which in some cases can lead to single step polishing. And you can see here some distribution data from cut length on a number of fibers. So we get average cut lengths from 20 to 25 microns on an MU connector. So that's a 1.25 millimeter series, and typical tolerances of plus or minus 5 micron to 1 sigma. So that consistent short cleave length leads to higher yield, less polishing, and because you're using less harsh grits typically, you end up with better return loss characteristics. If you look at the process flow, which we show here, we can take out a couple of the cleaving and polishing steps, so it leads to far increased workflow efficiency. And we've had many customers that have actually bought a laser cleave system instead of buying an additional polishing system, because that's allowed them to massively increase their throughput. So you're probably asking yourself, this is 20-year-old technology. Why are we talking about this and what's new? Well, actually, over the last few years, we've completely refreshed, renewed our product line and introduced some new tools. One of those being the LCS 500, which you see here. This allows us to have low flare ribbon processing, suitable for placement into V-grooves, silicon, photonics, and co-package optics. One of the problems traditionally with laser cleaving is that the heat of the process, because it is thermal as well as ablative, led to thickening of the fiber at the cleave end. In the LCS 500, we've managed to overcome that. You can see the process here, where we cleave the fiber and then strip the buffer and then insert the 125 micron 12-way fiber into an MTP connector. So you can see the stripped fibers, and here you can see insertion into the connector. Traditionally, you would have had a lot of fiber sticking out the end here, as in this example here. But because we've done everything with laser and we're now able to control the lengths very accurately, you can put this straight onto your curing fixture and then directly onto the polishing machine. We also supply tooling to do dual row, and I mentioned on the first slide where we talked about the rounding effect. The rounding that you actually get helps feed this in to the MTP connector. As well as connectors, we also offer direct connection to devices, be that active optical cables, silicon photonics, PICs and V-grooves, and you can see some examples here. We get very low flare processing, angled cleaves from 0 to 50 degrees. Those could be referenced to something like metallization, strip shoulders, and most recently we've been able to show processing of 127 micron pitch here on Panda fiber. There's some more photos here from an SEM of actually the fiber, and again, see how the fiber's not fattened near the cleave area. You do get a bit of silica redeposits just around the edge, and we can cleave features on our systems relative to Panda fiber stress rods. All this allows us to make some quite complex assemblies. So here you see a very small LC part for installation in an SFP package, where we laser strip the acrylate. We then laser cleave the part on our 3500 platform, and you'll note on the cleave how square the edges are. And that allows us to go into a fusion splice. In this particular application, We do a diffusion splice, so we couple an SMF28 fiber up to a high numerical aperture fiber and then diffuse the germanium core, so you have an adiabatic taper. We put a glass block to protect that splice and then cleave the fiber at the end, so it can then be used in a pick and place machine to align to the chip. We've also used this technology as well as pit coupling to make small collimators and isolators. This leads very well into our assembly plant, which Alan mentioned in Greenville, South Carolina, where we do V-groove assembly, waveguide and PICs, and lens collimators array. Here you can see a PM array that we've done in V-grooves with 20 fibers. And there's more details about this on our webinar given about a month ago that's available on our website. As well as doing cleaving, we can also do stripping of optical fiber. And here we've developed a tool to actually do stripping on ribbon fibers. So it's rapid non-contact processing, it's accurate and repeatable to features, chemically free, and it gives improvement performance and increased yield, especially when comparing to mechanical methods, where it's very easy for the blades to actually either chatter along the fiber or create nicks. It's very high throughput. We're taking less than a minute to process a 50mm strip, and we can see an example of that here. So hopefully what I've shown is OpTek is at the forefront of fiber processing technology. We have many platforms and modules to meet your processing needs, and if we don't, we'll develop one. 20 years ago, when OpTek was formed, we supported the telecoms revolution, and today we're here supporting the AI and quantum revolutions. Here's an example of some of our platforms, and I'd like to move to questions. Thank you for listening.
Thanks, Chris. That was an excellent and insightful presentation. It's always great to see the depth of innovation and technical expertise coming from the OpTek team. Now let's take a look at some of the questions that have come in from our audience. So firstly, Chris, could you explain how being contact-free and not prone to tool wear helps improve long-term stability compared to mechanical cleaving?
Yes, the process is more stable. So on mechanical cleaves, as the blade wears, the scratch becomes less sharp and that it just doesn't propagate as well under that tension. It's not a problem for the laser process because actually we use a thermal ablative process, so it's very different.
Okay, great. What's the shortest cleave length achievable on the LaserCleave 1500 and how tight are the tolerances across different ferrule types?
So it really does depend on the connector geometry. 20 microns is typical for 1.25mm series, so LC and MU, and that's really required for single step polishing. Because of the system design, some small protrusions are always present, but I'd be happy to take that offline and discuss with you. Yeah, the needs in more detail.
Fantastic. Okay, another one in. How easily can the LaserCleave process be integrated into existing connector assembly or polishing lines? Does it need new tooling?
From the workflow slide I showed, so maybe I can go back to that. You can see the tools are really designed to go into your current production line. If you want to make it more integrated, that's possible as well by introducing strip tools, cleave tools. But yeah, it will work with your current process flow. Okay.
Is there a diameter limit for laser cleaving of optical fibers? Could you laser cleave fibers between 500 and 1000 micron?
So that's an interesting question. And the answer is yes, we can. The 3500 series off the shelf will do up to about 600 microns. To get up to a micron with an optical quality finish, we need to deploy some tricks. So we probably need to understand your requirements in more detail. So if you can send us that through.
Okay, fantastic. Can the LCS 500 process both simplex and ribbon fibers without major setup changes, or does it require separate fixtures?
So the LCS 500 is mainly designed for ribbons and a very specific job. If you want to process other connectors like simplex, I would push you at other platforms like our LC 1500, which has a wider variety of tooling. But yeah, again, we should take it offline in discussions.
Okay. How does the laser stripping process avoid damaging the cladding, especially when working with polyimide coated fibers?
So by careful control of the process, we actually use different processors and lasers to strip acrylate and polyimide. So in the polyimide example you mentioned, we're no longer using something that's absorbed in the glass. And yeah, that's how we can ensure that it avoids damaging the cladding.
Cool. A couple more just popped in. Is the active feedback during lens machining mainly for controlling geometry, or does it also help with optical alignment, like for PM fibers?
So yes, the active feedback, the video system we have in allows you to control orientation of the lens with regard to PM, which is very important for cylindrical lens form. In regards to geometry, we have a far field monitor and we know what aspect ratio, what you tell us what aspect ratio you want, and we trim the lens to match that aspect ratio, hopefully giving you much better coupling than you would achieve by polished lenses.
Okay. I think that, oh no, we've got another one in. For co-packaged optics and silicon photonics, how accurately can the LCS 500 control fiber protrusion during cleaving?
That really needs further discussion because we need to know what you're coupling to, what waveguides. Yeah, perhaps we can take that offline.
Yeah, we'll get back to you, whoever answered that, later on. And finally, last one just popped in. Since the LaserCleave technology has been around for a while, what's new in the current systems that make them more relevant today?
The biggest change, I would say, is the focus shift to multi-ribbon fiber connectors and multi-fiber connectors. That has driven us to reduce the flare and mushrooming that was previously a hurdle to adoption of some of this technology in those applications.
Okay. That's all the questions we have today, and that brings us to the end of today's session. We hope you enjoyed this fourth installment of the OpTek webinar series. A big thank you to Chris for sharing his knowledge, and to all of you for joining us. The recording will be available shortly, and we'll be back in 2026 with a brand new series of webinars, and we look forward to seeing you then. Thank you.